Jordan, what are the two types of charge that we have? Right. Positive comes from having more of what than what? Christine, positive comes from having more of what than what? Good, more protons than electrons. And negative comes from having more what than what? Natalie? Good, more electrons than protons. So we've established that we have positive and negative charge. How do we get that positive and negative charge? How do we get more protons than electrons or more electrons than protons? Well, we learned yesterday that there's two ways of charging objects. What are those two ways of charging objects? What's the first way? Michael? Conduction. Second way is induction. Good. What's the main difference between conduction and induction? We talked about a couple of differences yesterday, but one of them is the big one. Conduction always involves this. Induction never involves this. Good. Conduction always involves a transfer of charge. Induction never involves a transfer of charge. So no charge transfer. Now, conduction usually involves what? Conduction always involves a charge transfer, but it also usually involves what? Yeah, it usually involves two objects touching each other. Well, no, not always, but usually it does. Induction never involves two objects touching each other. What are the two subcategories of conduction that we talked about yesterday? The two ways of charging via conduction. Dylan's on fire today. Go ahead, Dylan.
Friction and contact.
Good. Charging by friction, charging by contact. What's the difference between charging by friction and charging by contact? These are the easy ones, by the way. We charge by induction, it's a little bit harder. So if you know the answer to this, get it out of the way. Give me the answer to the easy questions, and then maybe I don't call on you for the harder questions. What's the difference between between friction and contact? Yeah, good. Friction is when you rub two things together. And then those two materials that you rub together have to be dissimilar materials. That means they have to be materials that are different. One object will gain electrons, one object will lose electrons. Okay, one object becomes negative, the one that gains electrons, the one that loses electrons becomes positive. Okay, that's charging by friction. The energy, the kinetic energy from the rubbing, causes the electrons to leave and go to the other one. What about charging by contact? Yeah, we just simply touch them together. Now, these two materials don't have to be different, but they do have to have a different charge. If you touch two things together, one's 0 and one's +5, they're going to balance out to be 2.5 and 2.5. You touch two things together that are both +5, they balance out to be +5 and +5. You haven't done anything. So in order to charge by contact, you have to have two different amounts of charge on your charging objects. The other thing that we call charging by contact sometimes, by the way, sometimes we just call it charging by conduction. We call it by its umbrella term. Some people don't like to call it charging by contact because it doesn't necessarily have to have contact in order to be charging by contact. So some people just prefer to call it charging by conduction, even though it's the same thing. Some people find the term charging by contact just is a little bit misleading sometimes. So you might see either one, charging by contact, charging by conduction. What about induction? What are my two subcategories of charging by induction? Jared? Good. We can induce induction. We can induce a temporary separation of charge. And of course, the other one's going to be a permanent charge, right? It's not a separation. It's just a straight permanent charge. Let's say we have a neutral object here with 3 positives and 3 negatives. We bring a negatively charged object nearby. What happens to the protons in this neutral object? What happens to the protons here? They stay there, right? Nothing happens to the protons. Something happens to the electrons, though. They're free to move because they're not tightly bound to the nucleus like the protons are. Where do the electrons go? Jordan? Good. These electrons are going to be pushed away from the negative. Now, if you count up the number of negatives and positives on this neutral object, it's still neutral. 3 positives and 3 negatives. But you can see that the charges have separated now so that one side has a net negative charge and the other side has a net positive charge. Notice the side that's closest to the charging object is oppositely charged to the charging object. The object that we brought nearby is negative. The side that's closest to it becomes positive. Watch what happens now when I draw the other scenario. The other scenario in which we have a neutral object with, let's say, 3 positives and 3 negatives again, this time bringing a positively charged object nearby. What happens to the protons here, Carissa? No? Yeah, the protons stay where they are. The electrons are going to move towards it, right? Good. The electrons move towards it. So now we're going to have a bunch of negatives on this side. Still neutral overall, right? Still 3 positives, 3 negatives. But now, once again, we have that separation. This time, the left side being positive and the right side being negative. Notice again that the charging object is oppositely charged to the side of the neutral object that's closest to it. So the side of the object that's closest, the charging object is negative, the charging object itself is positive. That's always going to be the case. No surprises there, no tricks there. When you bring a charging object nearby a neutral object, the side that's closest will always be opposite charged. And that's why charged objects attract neutral objects. We bring a negative nearby neutral, the side that's closest becomes positive, so it attracts. We bring a positive nearby, the side that's closest becomes negative, so that's why it attracts. Jordan, question? Okay, good question. Why don't the positives move away when the positive comes closer? The positive particles, the protons, are tightly bound in that nucleus by that force that we call the strong nuclear force. Now the electrons are orbiting around, and they're held in place by the electric force, but the electric force is a lot weaker than that strong nuclear force. So it's possible to get protons to leave an atom, but not by rubbing 2 things together or by touching 2 charges that are different. You're not going to do it that way. It takes a lot more energy to do it than that. That's what we call a nuclear reaction as opposed to some kind of electrical interaction. So it's not going to happen in this unit. It'll happen in our last unit. Okay, but we'll tell you then how that happens. Okay, let's make it permanent now. Let's take my neutral object. Let's bring my negatively charged object nearby. Of course, the positives stay where they are, just like they did in the last example that I gave you. The negatives get pushed to the left-hand side. It's exactly the same as we have in diagram number 1 on the left-hand side. But as soon as we introduce this ground wire, which could be literally a wire that goes into the ground, or it could be something as simple as touching it to something big, something that can take or give electrons. These electrons are now going to be pushed a little bit further away down into the ground. So now we have not just electrons being pushed to the left-hand side, we have the electrons being pushed to the left side and out of the charged, or out of the neutral object. That leaves us now with a net positive charge on this entire object. That, however, is going to go back to the way that it was before, neutral, if I take this object away. The key here is to cut that ground wire before I take that charging object away. When I do that, I'm left with a net positive charge on that neutral object. Notice that it becomes positive. Notice that the object doing the charging was negative, oppositely charged. Let's draw one more picture here. This time, let's say we have a neutral object. And this time we're bringing a positively charged object nearby. Prediction. What's the charge on this neutral object going to become after we ground it? If I brought negative nearby, it became positive. If I bring positive nearby, it's going to become negative. Why is it going to become negative? Because these negatives that are already present inside this neutral object are pulled to the right-hand side. Going to look like this. But you also get electrons in the ground, or whatever is attached to it, get pulled up to this neutral object. So you get a whole bunch of extra electrons in there. Now, if I take this charging object away, they just go back into the ground and it behaves, looks like it did before. But if I cut this ground wire before I take that charged object away, then this is going to stay negatively charged. Does that make some sense? Yesterday we talked about 3 real-life examples. One, not so much real life, I guess, the fridge stove thing. Touch the fridge and the stove at the same time, or at least my fridge and stove in university, and got that shock. Okay, we explained how that happened, but we also talked about that electrostatic precipitator. Remember that? A precipitator, that air cleaner. You had some charged conducting rods here. They were charged negative. And then you had these positively charged conducting plates. The air, along with the dust, would go through this whole apparatus. And that air, along with the dust, would touch these negatively charged plates. What happened to the dust particles as these neutral dust particles touched the negatively charged rods? They became negative. Negative by what? Conduction or induction? There was charge transferred from these rods to these neutral dust particles. That's conduction, because charge was transferred, right? So you get conduction taking place in here. Now you've got this air with the dust particles still going through. But now the dust particles are negative. What happens to them when they go through these positive plates? It sticks to them, right? It gets attracted to them and it sticks to them. What comes out the other side? The air, minus the dust particles that stuck to these positively charged plates. Now you can imagine every once in a while you're going to have to take these plates and clean them, right? Because after a while they're going to have a whole bunch of dust particles stuck on them. But that's not such a big deal. Okay? The other scenario, or another example that we used yesterday, was that electrostatic paint gun. Doesn't look much like a paint gun, but let's pretend it is. You know what I mean here. Inside this electrostatic paint gun, we have this rod that's charged positively, and that's done by a power supply, right? We can charge it positively by a power supply. As the paint goes by this and touches this positively charged rod, what happens to the paint? It becomes positively charged. Neutral touches positive, they balance out to be positive and positive. Conduction or induction? No, conduction, because there's a charge transfer. This time it would actually go from the paint to the rod, right? Because that's positive. If they both become positive, the paint was neutral, it's become positive, it must have lost electrons as opposed to gaining protons. So the paint comes out of there, it's charged, it's positively charged, and then we spray it against our metal fence, or we spray it against our metal car, or we spray it against our metal anything, our conducting anything that happens to be grounded. And these positively charged paint particles get attracted to it. So not only are you spraying paint right at it, even the paint that's not sprayed right at this metal gets attracted to it and gets pulled towards it. So you get very little overspray here, very little mess made here, because most of the paint just gets attracted right to it and sticks to it. You also lose a lot less paint, so it becomes a lot cheaper if you're spraying it electrostatically. I think when they paint cars, brand new cars, like at the factory, I think they use an electrostatic process. Again, they're looking for any way to eliminate costs, right? So if you can waste less paint by having all of the paint, hit the car, then you're a lot better off than if you lose half of the paint because half of it hit the wall and half of it hit the car. What's a real-life example of induction? What a great question. How about you take a look at this one, okay? All right, you've had a chance to work on it. What's the answer to the question? Who says A, positive by induction? Who says B, negative by induction? C, positive by conduction? D, negative by conduction? Okay, most people said A. Let's take a look at it here. The top of this cloud is positive, but it's the bottom of the cloud that we're really concerned about because the lightning bolt comes from the bottom of the cloud. So you've got essentially a cloud that's charged negatively here. That's the part that we're concerned about since that's the part that's closest to the ground. The Earth is neutral. Equal number of positives and negatives. What happens to the protons in the Earth when it's exposed to this negatively charged cloud? They're going to stay there. What happens to the negatives in the Earth? They're going to get pushed away. They're going to get pushed downward. So now you have a situation that looks something like this. The top of the Earth becomes charged positively. We knew that would happen, right? We didn't even really need to draw the diagram. We could have just remembered the diagram that I drew in class a few minutes ago. The side of the object that's neutral always becomes charged opposite to the thing that's doing the charging. So if I bring a negative cloud nearby, the top of the Earth is going to become positive. Now, what's that process called? It's induction, obviously. Why is it induction? Yeah, it's a temporary separation of charge. What isn't happening here that would make it conduction? A transfer of charge. You're not transferring charge here, right? Yes. That before word is really important there. Before the lightning strike, this is induction because you're not transferring charge. But after would be conduction. Let's take a look at this one. So what's the answer to this question? Who got A? Who got A, negative by induction? Nobody? B, negative by conduction. Okay, C, neutral by induction. D, neutral by conduction. Okay, the answer is B. You're correct. We have a cloud here that the bottom of which, this is where the electrons come from, is negatively charged. Okay, we've got this tree that's receiving electrons from the cloud. If these electrons come down from the cloud to the tree, then the top of this tree is going to become negatively charged during the lightning strike. It receives electrons. It has to become negatively charged. So the answer has got to be either A or B, negatively charged. Why is it conduction as opposed to induction? Not because it's touching. No, the cloud isn't touching the tree. There's a transfer of charge here. It's funny you said that, Jared, because in all three classes I've asked that question, and all three classes I've got the same answer. It's touching. We don't. What I want you to be careful of here is that you don't look at a question that you know the answer to because I've told you the answer, and then kind of look for a justification for that, right? We want to fundamentally go back to it and say, like, you know, why is it, right? Let's think about why it is as opposed to just trying to remember something that we said in class that might kind of fit. Okay, why is it conduction? Well, it's not touching. You know, it's not touching. So what is it? It's got to be the fact that charge is transferring. Okay, the lightning bolt, I think maybe the lightning bolt confuses people. You know, the lightning bolt is touching the tree, but the lightning bolt is just the electrons being transferred, right? The two objects doing the charging, the tree and the cloud, aren't touching each other. Now, here's a quick question for you that's kind of an aside to this, but kind of related. Why is it that we get this lightning when it's raining more often than when we get it at other times? You got a cloud up there, and you know, obviously you tend to have more clouds when it's raining, so that might be one reason. But even if you have clouds on a day when it's not raining, you generally don't get lightning. Why do we tend to get it on rainy days, on moist days? Because water is a good conductor, right? The moisture in the air provides an easier path for electrons from the cloud to the ground. That's why we don't see lightning storms in the middle of the winter. The humidity in the wintertime is a lot lower, so it's a lot less probability. The clouds would have to be so close to the ground and still be charged in order to cause lightning in the wintertime when it's drier. Okay, here's a new thing for you. Still related to what we did yesterday, but we didn't talk about this specific term yesterday. An electroscope is a device that detects charge. The two pictures on the board right now are both examples of electroscopes, both examples of devices that detect charge. Devices that tell us whether we have charge or not, but don't tell us how much charge we have or what type of charge we have. So it's not overly useful in that sense. You got a positive charged object, all right, it'll tell us that it's charged, but it won't tell us that it's positive. It's really charged, like a lot, all right, it'll tell us it's charged, but it won't tell us that it's really charged a lot. Here's how it works. Here's how both of them work. They're both basically the same. In both of them, we have this steel or copper or anything conducting ball on the top. It's connected usually to a copper rod that goes down through the middle, or some kind of conducting rod that goes down through the middle, which is in turn connected to a couple pieces of foil, really, really thin, really, really light foil that are free to move about really, really easily. Let's bring a positively charged object nearby the ball on the top of this electroscope. What's going to happen to the protons in the ball of this electroscope? What's going to happen to the protons inside the rod of this electroscope and inside the leaves of this electroscope? Nothing. Nothing happens to the protons. It never does. They want to be pushed away, but they can't be because they're too tightly bound in that nucleus. So they're not. What happens to the electrons? They're going to move towards it. So you had protons and electrons scattered throughout. Now we've got electrons being pulled up into this ball. This ball then becomes negative, right? What do the leaves become? They don't have any more positive charges than they had before, but now they have less negatives. So the net charge on both of these leaves is still going to be positive. What happens to these leaves now that they're both positive? They're going to repel each other, so they spread apart. There's the detection of the positive charge. If these leaves spread apart, there must have been charge on that object that I brought nearby. Let's try bringing a negative nearby and see what happens. What happens to the protons in this electroscope? Stay the same. What happens to the electrons? They're going to get pushed down. So that means this ball is going to become positively charged because it loses electrons, and these leaves are going to become negatively charged because they gain electrons. What happens to the leaves? Nope. They repel because they're both negatively charged. Like charges repel. So in both cases, when I bring a positive rod or a negative rod nearby, the leaves are going to repel. Remember what we said a minute ago? It detects charge, but it doesn't tell you what kind of charge you have. So you can bring positive or negative nearby and you get the exact same result on the electroscope. Now what would happen if I grounded this? If I grounded the left one, we would think that these negatives would get sucked up from the leaves of this electroscope into the ball, and then we could maybe get a bunch of negatives from the ground get sucked up into this ball as well. We would, in fact, get electrons from the ground get sucked into this ball, but they couldn't all stay in the ball. So what ended up happening is that the entire thing would end up being negative, including the leaves. So you'd find that the leaves would spread apart here, but this time not because they were positive, but because they were negatively charged. What would happen, though, if you took this charging object away? Too many electrons on there, they'd go back. They'd go back into the ground. The ones that came up would go back. If we cut this before we take the charging object away, then these leaves are going to stay spread apart, even after you take the charging object away. Not forever, because eventually the electrons are going to arc to the air, discharge to the air. But they're going to stay spread apart for a while. What's going to happen over here when we ground it? This time, the electrons that normally would go down into the leaves, this time are going to be pushed down into the ground. That's going to leave the ball of the electroscope positive again, but it's also going to leave the leaves of the electroscope positive. They're still going to spread apart, but they're going to spread apart because they're positive this time. Cut this, they stay spread apart because there's no way for the electrons to go back into the electroscope from the ground now. Even after I take this object away, this entire electroscope will still be positive and these leaves will still stay spread apart. That make sense? Another application, okay, another good application. It's not as practical and maybe as interesting as how you paint a fence and not get any overspray. Okay, but it's still an example of the type of thing that you could see sometime on a test. This is actually a specific objective we have to know about electroscopes. Painting fences isn't, but it's a good example of something that we could see at some point. All right, there's a few questions that I want you to work on page 523. I'll give you a few minutes, maybe about 5 minutes, to work on those questions right now, just to get a bit of a start. The questions that I want you to do on 523 are numbers 6 to 10 and 12. So let's take about 5 minutes, see what we can get done, and then we'll move on to the next thing. We're going to move on here, and I'm going to ask you to finish the questions that you haven't finished already for homework tonight, please. One more question, though, that I do want you to work on in class here. It's multiple choice question number 36 from your booklet. Give you 30 seconds to work on that, and then we'll take a look at it. All right, what's the answer to question number 36? Who says A? A? B? C? D? Okay. The distribution of the charge on the rod is, we're saying, negative at end x, and the electrons move onto the rod from the ground. We've got a positively charged object. We have this metal rod here, xy. What's going to happen to the protons on this rod xy as a result of this positively charged object? Nothing. What's going to happen to the electrons? They're going to get pulled up here and attracted to end x. So what's end x going to be? Negative. It's going to be negative by conduction or induction? We're not asked that, but is it conduction or induction? It's a tough one. Jordan, what did you say? Induction, conduction. The answer is actually induction. Induction. This is the object doing the charging. It's not touching, and it's not transferring charge. Now, there is a transfer of charge from the ground to this charging object. So you look at that and say, well, if there's a transfer of charge, that's got to be conduction, right? In a sense, there is conduction happening within this, but the overall process would still call induction, because the object that's causing the charging, the object that's doing the charging, isn't touching, and it's not transferring charge. So the answer would be induction if we were asked that. And you can see that the electrons are moving from the ground into the rod. So the answer is, in fact, D. Good. We're going to shift gears a little bit here and start something new today. Still, obviously, electricity related, but not the whole charging by induction, conduction, that type of thing. Physics 20, you learned about a law called Newton's law of universal gravitation. It gave us the relationship between the gravitational force that acted between two objects and the distance separating those two objects along with their masses. The equation that described Newton's law of universal gravitation looked like this. I think you guys are going to remember this. At least I hope you do. How many people recognize that equation? The value of g, that was a constant. Its value is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Now, this is not the topic that we're going to do today. Don't get this mixed up with Coulomb's law and Coulomb's torsion balance experiment. I just want you to remember that as we talk about Coulomb's law, because you're going to find in just a few minutes that there's a lot of similarities between Coulomb's law and Newton's law of universal gravitation that we did last year. Coulomb's torsion balance experiment was an experiment that was performed in order to derive the relationship between not the gravitational force and masses, but the electric force and charges. The experiment, simplified somewhat, looks something like this. You got a string hanging from the top of a box. On the end of that string would be a rod. There's a couple of objects on either end of that rod to keep it balanced from kind of tipping over. One of those objects is going to be charged. We'll give it a charge that we call Q1. We're going to bring another object nearby. We're going to call it Q2. Q2 is either going to attract or repel Q1, and it's going to cause that string to twist a little bit, one way or the other. Coulomb would have done a number of experiments here, in each of them measuring the value of R. R is the distance that separates these two charges. And that's a pretty easy thing for him to measure. He would have also measured the value of Q1 and Q2. Now, be careful with this one. He wasn't able to measure the value in coulombs of these two charges, but he was able to measure the relative values. How do you measure the relative values? He starts off with a big object that has a charge of Q. Then he touches a neutral object to it. What does this charge become then? Neutral and Q touch each other, and they become 1/2 Q and 1/2 Q. Then he touches another neutral object, and it becomes a 1/4 Q. Another one, it becomes an 1/8 Q. And another one, it becomes a 16th Q, and so on. So he's able to manipulate the value of these charges without knowing what the actual values of the charges are. It's kind of like variable value changing in a way, right? He's manipulating the value of a charge without knowing what the value was to begin with. Just keeps cutting it in half each time. So he's able to get the relative values of Q1 and Q2, and he's able to measure the value of the force, or at least the magnitude of the force. That's the tough one. All of you at some point have been on a swing set, and all of you at some point have twisted that swing set up so that when you lift your feet up off the ground, you start turning around and spinning really, really fast. All of you know at some level that as you twist that more and more and more, it becomes harder and harder and harder to twist. More and more force required to twist it. You could, if you wanted to, do an experiment to determine how much force was required to twist it a certain amount. You twisted 1 revolution, well, how much force did that require? 2 revolutions, how much force did that require? And so on. Coulomb could do a similar thing with this. He could determine how much force was required to twist the string a certain amount, how much force was required to twist it a different amount, and so on and so on. When he does this experiment, brings Q2 near Q1, he finds that the string twists. Based on how much it twists, he's able to determine the value of the force. Twist 10 degrees, all right, it must have been this much force based on previous experiments. Just like you, when you twist yourself on that swing set, could, if you wanted to, determine how much force was required to twist it a certain amount. All right, now Coulomb performs 3 sets of experiments. In the first experiment, he manipulates the value of Q1. He keeps changing the value of Q1. Responding to that is the force. What would be the control variables here, by the way? What does he have to keep the same in this particular experiment when he's manipulating Q1 and responding to that as F? What's got to stay the same? No? Okay, that's related to the force. What's got to stay the same if he's manipulating Q1 and responding to that as F? I'll give you a hint. It's staring you right in the face. R, he's got to keep the distance separating them the same throughout that experiment. He's also got to keep Q2 the same. So my control variables here would be Q2 and R. When he does that experiment, manipulates Q1, responding F, gets a relationship between those two variables, he finds that F is directly related to Q1. It's a linear relationship. As Q1 gets bigger, F gets bigger. Well, then he does another experiment. This time he manipulates Q2, responding to that as the force. What would be my control variables in this one? Q1 and R. We got to keep all the other relevant variables the same. This is also a linear relationship. That also told him that force is directly related to Q2. As Q2 goes up, F goes up. Finally, he performed an experiment where he manipulated the value of R, measured the value of F that responds to that. This time you get a graph that looks like this. My control variables here would be Q1 and Q2. And the relationship that Coulomb would have got from this would have been one that we call an inverse square relationship. As R goes up, F goes down. That should make some sense to us, right? If you have two charges and they're further apart, the force that acts between them is going to be smaller. Now, Coulomb would have put these three relationships together to form an equation. The force that acts between two charges a certain distance apart is going to be directly related to Q1 times Q2, both of those are on the top, over R squared on the bottom, as you can see from the relationship above. So as the product of Q1, Q2 over R squared gets bigger, F gets bigger. To make that into an equation, we have to get rid of that proportionality constant. Instead of being F is proportional to Q1, Q2 over R, it's going to be equal to a constant times Q1, Q2 over R squared. That constant is what we call Coulomb's constant, and it has a value of 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Remember Newton's law of universal gravitation. F is equal to G m1 m2 over R squared. G was 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. You can see the similarities between these two forces. They're both what we call inverse square relationships. The structure of the equation is exactly the same. The magnitude of the forces isn't. The electric force will almost always be a bigger force than the gravitational force. We know that because the constant is so much bigger. 10 to the 9 versus 10 to the minus 11. This equation that we just derived here is Coulomb's law. Just like Gm1 m2 over R squared was Newton's law of universal gravitation. It provided for us the relationship between the masses and the distance separating the masses along with the force. This one provides for us the relationship between the force and the charges and the distance separating the charges. Got a little summary chart on the next page here. Coulomb's law, that's the new one that we just did today. Newton's law of gravitation that we did last year. They're both what we call inverse square relationships because F is related to the inverse related to the square of the distance that separates the charges or the masses. The magnitude, well, the electric force, the Coulomb's law force, tends to be a big force, whereas gravity, although we think of it as a big force, isn't really very big. Gravity, in the grand scheme of things, is a very small force. There's 4 fundamental forces that exist in the universe. Gravity is one of them. Gravity is the smallest of the 4. We think of it as being big because, well, when you step off the edge of a building, you fall. But you only fall because the mass of the Earth is so huge that it gives you a big force. Not because fundamentally the force is big, but because you have such a massive amount of mass causing that force. It takes a lot less charge to cause a big electric force than it does mass to cause a big gravitational force. Finally, direction. Well, gravitation is only attractive because you've only got one kind of mass. Mass is mass. But Coulomb's law can be attractive or repulsive because we can have 2 types of charge. We can have positive charge, we can have negative charge, resulting in either attractive or repulsive. Let's take a quick look at an example here now. It says a small metal sphere with a negative charge. Starting circling things again, right? It's been a while since we've had to do this because it's been a while since we've done problems. We've got a negative charge here, and we've got another positive charge. We've got a distance that separates them at 3.30 centimeters. Those are all odd things that could lead me to silly mistakes. We've got positive, we've got negative, we've got centimeters rather than meters. We're going to find the force. So Q1, we're going to say is negative 2.10 times 10 to the minus 6 coulombs. Q2, we're going to say is positive 1.50 times 10 to the negative 6 coulombs. We're going to say that R, the distance that separates them, is 3.30 centimeters, or 0.0330 meters. And we want to find F, the magnitude of the force and whether it's attractive or repulsive. The basic equation that applies here is our Coulomb's law equation. K, Q1, Q2 over r squared. 8.99 times 10 to the 9 times 2.10 times 10 to the minus 6 times 1.50 times 10 to the minus 6. We divide that by the square of the distance. A really, really common mistake here, and I guarantee if this is a multiple choice question, that mistake will be one of your options. Forgetting to square that r. Don't forget to square that r. I'm telling you that right now. There's 8 of you, but in all likelihood, at least 2 of you on your unit test will forget to square that r. Don't be one of those 2. Yeah, always got to be in meters, right? Standard units. No, it's 3.3. 3.3. So we divide 3.3 by 100, we get 0.033. Hey, what did I not do here in this equation? What did I leave off in this equation? A negative, right? Didn't I circle negative so I wouldn't forget? Here's the thing, and remember this, please. I don't want you to ever plug in a negative sign into an equation indicating negative charge. For us, negative means direction. In an equation, that is, negative means direction. This negative isn't a direction. It's a sign of a charge. Don't plug in a negative for a charge into an equation. Now, it's still important to circle it because we're going to need that later on to determine whether it's an attractive or repulsive force. But we don't need it in the equation. Not only do we not need it, we shouldn't put it in there. When we do the math there, we end up getting 26.0 newtons. We know that it's a 26.0 newton attractive force. Because one charge is positive and one charge is negative. Now is when we need to know that it's negative, right? Not when we did the equation. That's going to stand today and every day for the rest of the year. If you plug the sign of a charge, if you plug a charge value into an equation, do not use its sign. For us, in an equation, negative simply means direction, not sign of a charge. Let's take a look at one practice problem on page 530. You can finish that up. You can work on that right now if you want, but you've also got some time tonight to work on it for homework if you want. Your homework tonight is page, check and reflect questions, page 523. Number 6 to 10 and 12. In addition, you get your practice problems on page 530. There's a 530, I guess it is. There's only one of those. Right? See what you can get done over the next 4 or 5 minutes here in class, and maybe have no homework tonight. Other than this, that's it for today.